In this video, we're going to walk through how to validate a mechanism. Now, there's two different ways that you'll find yourself in a position with these types of problems. One, you'll have a slow first step, or two, your slow step will be one of the later ones, the later steps in the mechanism. Now, the simpler version is when your first step is slow. So we'll talk through that first, and then we'll go through the more complicated examples of fast first steps. So whenever we're validating a mechanism, we're not proving it, right? We're validating it, which just means this is reasonable. We need to make sure that two conditions are met. One, we need to make sure that the elementary steps add up to the overall reaction. So that's number one. If they don't add up to the overall reaction, then we can't even really begin to do more work on this because we just have a different reaction. And second, the rate law that's predicted by the mechanism needs to be consistent with the experimentally observed rate law. And so this is going to take two steps. This is going to be one, predicting the rate law from our mechanism. And two, it's going to then be determining the experimental rate law and comparing it. So let's walk through an example. So we have the overall reaction here of hydrogen peroxide decomposing. Two hydrogen peroxide molecules will become one oxygen and two water molecules. And there is a proposed mechanism here for this decomposition. This is the decomposition in the presence of a catalyst. And so here's where the catalyst is. It's something that is a reactant and a product, and it reforms. So here is our catalyst. And this reaction will take place on its own without a catalyst, but it's really slow. If you add a catalyst, you can actually see it in real time. There's also an intermediate here. It's this IO minus. That's our intermediate. So first, I'm going to make sure that these sum up to the overall reaction. And so I'm just going to take the reactants of both elementary steps on one side and the products on the other side, and we'll cancel out anything that's the same on either side and see if we end up with the reaction we're interested in. So combining these, I see H2O2 plus I minus plus H2O2 plus IO minus. And that's going to go to, and I'm going to kind of come down here to save some room for the next step. That's going to come down to our products, which will be H2O plus IO minus plus H2O plus O2 plus I minus. So now we'll go through and we'll cancel anything that's the same on either side of the equation. So the I minus, both a reactant and product. I don't have H2O2 on the product side, so those will stay there, but I have this IO minus on the product side. And I think that's everything that cancels. So I can rewrite this as 2 hydrogen peroxide forms 2H2O plus O2. And that's the same as the overall reaction. So step one is validated. Now, step two of validating the mechanism would involve predicting the rate law for the based on the mechanism, and then comparing that to the actual experimental data that we can derive a rate law from. And so we're just going to do the first part of that step here of predicting what that rate law is. Okay, so to predict this rate law, we need to create a rate law for just the slow step. So the slow step is equal to the first step. We're told that in our mechanism. So that simplifies a few things. So that means our rate is going to be equal to the rate law constant, which we're not going to worry about calculating. That's something we would have to determine experimentally. And now I'm going to take the concentration of just my reactants of that first step. So that's H2O2 and I minus. The concentration of my reactant and the concentration of my catalyst. And so That's it. There's just a first order dependence on each of those because I just am using one hydrogen peroxide and one I minus. I don't have a 2 or 3 coefficient anywhere. And so that's going to be my predicted rate law. And so when I do a comparison, uh, what I'm looking for is a first order dependence with respect to hydrogen peroxide and a first order dependence with respect to I minus. All right, in the next video, we'll go through what happens when our slow step isn't our first step and it includes intermediates.